So in our criterion here for getting countable additivity, in this criterion flower, the compact class K can just be, might just be totally unrelated to the algebra of sets A. And so we get this sort of more complicated than we often want way of stating the criterion. It's not really that complicated when K is actually a subset of A. So when K is a subset of A, the criterion flower, in other words, K is an approximating class for mu, becomes equivalent to this other thing, which, let's call it leaf, which is much simpler. Just for every A, for every set that's in our algebra of sets, mu of that set is just the supremum, the biggest of these mu of k's, where the supremum is taken over the k's inside A that are in the approximating class. So notice that if you don't have K being inside A, then it wouldn't even make sense to say things like this, right? You couldn't evaluate mu at K's just because they're in fancy K. So mu is only defined on fancy A here. Okay, so I just want to verify that this is actually correct. So let's prove the statement made up here. So let's get the setup in place. A, an algebra of sets on X. K, a compact class, but now I'm assuming it's a subset of A. That's the crucial difference here. And mu, a non-negative additive function. Then I claim that flowers becomes equivalent to leaf. So suppose the condition that I called flower earlier is true. So that's this condition over here. In other words, the condition that K is an approximating class for mu. Then my goal is to prove leaf, so my goal here is to prove that mu of A is the supremum of this collection of real numbers. So let me actually write it like this, as supremum of a certain set. So what I was writing was a shorthand, or just an alternative notation for this, supremum of this set of real numbers, running over K in there with K contained in A. So two things to show. Mu of A is an upper bound for the set, and it's the least upper bound. So first, mu of A is an upper bound for this set. That's pretty easy. If K is a subset of A, then of course mu of K is less than or equal to mu of A, thanks to the fact that mu is an additive function. Where did I say it? Mu is an additive function on A, and mu is non-negative. So here we're using, again, that proposition 139. This is like at least the third time we use it in this lecture. Okay, so mu of A is definitely an upper bound, and then we have to show there's no lesser upper bound, so that mu of A is the least upper bound. So one way to do this is let epsilon be greater than 0. Then the goal would be to show, so then mu of A minus epsilon would be an arbitrary thing that's less than mu of A, right? And then the goal would be to show that this is not an upper bound. Anything less cannot be an upper bound. So we want to show that mu of a minus epsilon is exceeded by some element of this set. Well, now we can use flower. So by flower, there are k and b and a, such that k gets stuffed between b and a like this, and this region has a mu value less than epsilon. Then if you do mu a delete k, well, okay, so a delete k, since b is a subset of k, the complement of k is a subset of the complement of b, right? So mu of this is less than or equal to mu of this. Again, that's proposition 139 there, using the non-negativity and additivity of mu. We have this, and that's less than epsilon. And mu of a minus k, for an additive function, you've seen this a million times, that this is the same as mu of a minus mu of k, right? So mu of a minus mu of k is less than epsilon, and if you just rewrite that, that says, well, let me write the whole thing. So then this says that mu of k is greater than mu of a minus epsilon. And so we consider arbitrary epsilon greater than 0, mu of a minus epsilon is not an upper bound. This thing is greater than it. And this thing is in the set, is in this set. So that proves leaf. That proves that for every a, mu of a is this supremum. Oh, one horrible part of this proof is that I never fix a. I'm just talking about this a, but I never said where it came from. Okay, I think that's good now. And now for the other direction, that should be much easier. Now suppose leaf. Then we want to prove flower, so let epsilon be greater than 0 and let a be in there. So reminder, flower is this for every a, for every epsilon. Then we want to show that there's a k and a b such that this stuff happens. So remember, leaf tells me that about the supremum of a certain set. So by leaf, mu of a, if I take mu of a minus epsilon, then that's less than what leaf says is the least upper bound of a certain set. So this is not an upper bound. So this must be exceeded by some element of that set. So there is some element of that set, some k subset a with k in there, such that mu of k is actually greater than mu of a minus epsilon. Then just let b be k itself. Then we have this, just because k is already a subset of a and b equals k. And we also have, if you look at mu of this complement, then this is actually mu of a delete k, is mu of a minus mu of k, since mu is additive, which is less than epsilon according to this. So basically this, if the compact class that you're focusing on, if you make it be a subset of the algebra of sets, which is often a situation that you'll be in, then the condition flower becomes much easier to think about. The condition of being an approximating class for an additive function mu becomes just this. Just that basically that the class K has enough sets in it, enough of these K's in there, that if you just look at mu of K's, then those get really close to mu of A's for any A in the algebra of sets. So next time we'll look at some examples, and then if we also, so next time we'll look at some examples, and those will involve the some of our earlier attempts to get things to work in R and Rn with Jordan measure and things like that. And in those examples, we'll actually use compact sets for our compact class. And then if we still have time next time, we'll also start looking at what work has to go into extending additive functions to sigma algebras.